So when we did this interactive or a similar one, we learned that the pressure was dependent upon the collisions, right? So the number of times things started colliding. I don't really like this one as much because of this. But anyway, there you go. So that's colliding. And then if I add a different gas, it doesn't matter that it's a different gas. It's still going to contribute to the pressure because there's still more collisions. So any gas that's colliding will contribute to the pressure. And because of that, we have Dalton's law of partial pressures, which says that in a mixture of gases, each individual gas contributes to the total pressure and that total pressure is additive. Probably don't want to see that anymore. Okay. So what we saw there was a purple and a red gas, and each of them were giving some partial pressure to the total. In fact, if you want to see that even closer, um, watch this. So the purple gas is providing a pressure of, once it starts hitting, all right, so ballpark 18 point something. Let's go with 18.4. And then if I add the red gas, the total pressure goes up to 27.4, let's just say. So if the other one was 18.4, then the red gas is contributing 9 atmospheres of pressure so that the total is 27.4. So each individual gas is combining for the total pressure. All right. So a little thing, not in this class, but in college, might get you that the partial pressures have to match in their units. So we could give one in atmospheres and one in millimeters of mercury and one in kPa. You can't add them unless they're all in kPa or all in atmospheres or all in millimeters of mercury. Okay, so here we have three gases and we have a total. So the P total is 2 atmospheres and each partial pressure. So there's some hydrogen in there, and that's contributing 0.23. And there's some chlorine in there, and that's contributing 0.939. And so there's also some oxygen. And the question is what's the pressure of the oxygen? So the P total is going to equal the contribution by hydrogen plus the contribution by chlorine plus the contribution by oxygen. So all three of these gases exists and they're all contributing to the total. So in this problem, we have a total of 2 atmospheres. The hydrogen is 0.23 atmosphere, and the chlorine is 0.939 atmosphere. And so then the oxygen is going to be the rest, right? So anything that's not from chlorine or hydrogen must be done by oxygen. And so we just take 2 and subtract the 0.23 and the 0.939, and we get 0.831. So PO2 must equal 0.831 because then when you add up all those, you get 2 atmospheres. Okay, so the other reason we teach you this is if you do some labs, it's often a case where you'll collect a gas. So you'll do a reaction and a gas will form, and then that gas will escape through this tube and then collect over water. And we just do that so that we can see the volume of that gas that's produced. Okay, so so this could be like you had some zinc in here, and then you squirt some HCl, which is what this is doing here. Okay, so this is like HCl that you squirt into zinc, and then that forms H2 gas, and that H2 gas would then go up this tube, bubble through the water, and then collect up there. And you would get some pressure total up there. But here's the problem: water creates humidity. So part of this water will be in that atmosphere, and you'll have to subtract out what partial pressure water did at that temperature. So anytime you have a problem like this, we have to give you the partial pressure of water at different temperatures. Usually it'll just be given right out, like the reaction was done at 30 degrees and the partial pressure of water is 31.8 millimeters of mercury or whatever. But basically, it's the same concept that the total is equal to the dry gas plus the water. So in this case, we're telling you it's specifically water that's involved, as opposed to here, it could have been anything. In this case, it's specifically water. So here's an example. We give you a temperature, we give you the water pressure at that temperature. And so you just need to figure out, so the P total will equal the P dry, whatever the dry gas is, plus the water. And so in this case, neon is collected. The total pressure is 799. So our total pressure is 799.5 millimeters of mercury. We're trying to figure out what the dry gas is. And so we have to subtract out what the water pressure is at that temperature, which again is either given or you'll get a chart like this. And so that's just a matter of subtracting from 799.5 the 23.7, and you get 775.8. So that's how much the partial pressure of that gas is.